Welcome back, and we're going to begin with an example for this video. So it talks about a tank being filled with 30 gallons of water initially, and then we turn a faucet on to provide a constant flow of 3 gallons of water per minute into the tank. And so our first job is to determine this function V of t that gives the volume of water in the tank at t minutes after the faucet is turned on. And then it says investigate using a table, graph, and an equation. Okay, so I'm going to begin with actually a table. So if I think about t and V of t, okay, initially, so when time is 0, it has 30 gallons of water in it. Okay, then after 1 minute, right? How much water is going to be in the tank? Well, it's going to be 30. There's still going to be 30. It's not emptying. And then it increases its volume by 3 gallons because it says there's going to be 3 gallons of water added per minute into the tank. Okay, so 33. Okay, and then after 2 minutes, okay, it's going to be 33. It's not emptying, and then plus 3 more. So this is equal to 36. Okay, and you might start to see the pattern. 39 after 3 minutes, and 4 minutes it would be 42. Okay, so every time you are going, you are adding 3 gallons into the tank, right? When you see this behavior occur, the graph maybe won't surprise you, but if we look at a graph, and I'm just going to do the first quadrant, and I'm just going to make a sketch. I'm not going to do it precisely. Okay, so we have 30, and then I'm going to do 33, 36, 39. I'm just going to label 39, and then 42. Okay, and so I'm just going to not fill those in for the time being. And then 1 minute, 2 minutes, 3 minutes, and 4 minutes. Okay, and then what I'll see is, at 0 I have 30, so this is the volume. The vertical axis is volume and the horizontal axis is time. Okay, so 0, 30, 1, and 33 would be the next point. 2, 36, 3, 39, and then 4, 42. And what you're going to see is, and I'll maybe just do this I'll do this in green. You're going to see something that looks like that. Okay. Again, mine's a little off just because of my scale. I did it quickly. If I use actual grid paper, it would be a nice function, a nice linear function, right? And so if we wanted to make the equation now based on all this, okay, we can see that, okay, well, we need to figure out, it looks like a line, smells like a line, it probably is like a line, but we need to figure out, what is our slope and what is our intercept, okay? The intercept is actually pretty easy for us to determine, okay? This would be 30, right? Plus 30. We can see that just from the graph, okay? At time 0, it's up at 30, so that's our vertical intercept. That's our y-intercept, okay? And then so the only other thing that we have to determine is m, our slope. And so we could, go through and do the calculation, but I believe I can actually just read it off of the table. The slope is how much it's increasing by each time. Every time it's increasing by 3, okay? Okay, and so we get this nice volume function, and then so if we've answered part A, as an extension in part B, it's asking about the average and instantaneous rate of change. Now that might take a little bit of dusting off the cobwebs, but go back and review as needed for these two concepts. But average rate of change, okay, previously when we studied it, we said it was the slope of the secant line. Okay, that's generally what we did, but more generally, when we do the calculation of the average rate of change, it'd be y2 minus y1 over x2 minus x1, or if we were using function notation, it'd be f of b minus f of a all over b minus a. Okay, that's with function notation. Okay, and so if I were to pick any 2 points, okay, so now it's asking 0 to 2, 1 to 4, 30, or 10 to 30, okay, I can do this calculation, okay? I'll do maybe a couple, I'll do the first 2, and then I'll let you conjecture what it would be for 10 to 30. So now, just kind of separating my work, so from 0 to 2, okay, if I want to find the average rate of change, I'll talk about instantaneous here in a moment, but average rate of change, it would be f of 2 minus f of 0 over 2 minus 0, okay? Calculation-wise, let's see, this would be 36 minus 30 over 2, okay? And so that's 6 over 2, that just gives me 3, okay? And then if I do 1, 2, 4, and if I look at the average rate of change there, that'd be f of 4 minus f of 1 over 4 minus 1. Okay, so I get 42 minus 33 over 3. Okay, 9 in the numerator divided by 3 gives me 3. So do you want to conjecture what it might be from 10 to 30? 3. Yep, it ends up being 3. Okay, and you could actually talk about instantaneous rate of change, how much it's changing at any given moment. And for a linear function, these two things, instantaneous rate of change and average rate of change, are actually the same. Okay, and so that's what we really want to take away from all this. Average rate of change and instantaneous rate of change are the same for linear functions. Okay, and if you look at the value that we got for the average rate of change, that happened to be the slope. Okay, so in a linear function, this is super important. Make sure to star this, bold it, highlight it, or whatever you need to do for your notes. But in a linear function, average rate of change, instantaneous rate of change, and slope are all the same. So AROC equals IROC equals M. Okay, and so if we want to return to our base linear model, okay, f of x equals mx plus b, we can actually just say, okay, well, the m is going to be our rate of change, and then b is going to be whatever we start at, okay, assuming we're in a real world context, okay? And so just a quick concluding example, we have a linear function, we know it has an initial value of 5, and if you're thinking about a point, what does this mean if it has an initial value of 5? That means it outputs 5 whenever we input 0. Okay, that's what that language means. Initial value of 5. Okay, constant rate of change of 1/2. Okay, so this is AROC or IROC, doesn't matter in a linear function. That's 1/2. That's our m. Find the formula for this function. Okay, that's actually super quick. Let's do it. F of x is equal to mx plus b. And in this case, m was our rate of change, 1/2 x, plus b was our initial value of 5. There we go. And then sketch its graph. So I'm just going to do this in literally 10 seconds. So I'm just going to go up 5, and then let's see, I'll go up 1, So we have initial value here, and then a slope of 1/2 means we rise 1 and go over to the right 2. So there we have our basic quick sketch of this linear function. Okay, so again, big idea here. Linear functions have a constant rate of change, which we call the slope, and that is equal to the instantaneous and average rates of change.